Okay, so the last thing I wanted to talk about is the lattice energy of an ionic compound. Okay, and lattice energy is the energy released to form a lattice from gaseous ions. Okay, so it's a very, very specific definition. And so here, the definition is from gaseous ions. So we've got sodium plus, which is a gas, and chlorine minus, which is a gas, right? So these ions in the gaseous state to form sodium chloride solid. And that strict definition is what lattice energy is. And so you'll see that as delta H lat a lot of times. Okay, and that's in kilojoules per mole. And so, and remember this little knot right there is under standard conditions. So in, I think at the room temperature, 1 atmosphere of pressure, these things come together or these ions come together in the gaseous form to form the solid. Okay, and so the way lattice energies work is the bigger the negative number is, the more energy is released when formed. Okay, so I wanted to do kind of 2 examples of different ions. So if we have lithium and chloride, okay, and we take these 2 gaseous ions and we put them together to form lithium chloride solid, okay, it has a lattice energy of negative 834 kilojoules per mole. Now, if we take potassium and chlorine or chloride, and remember, these are both gases based on the lattice energy definition, we put these 2 things together to form potassium chloride solid. It has a lattice energy. So that says delta H lat of negative 701 kilojoules per mole. Okay, and so the question is, why are these 2 different? So chloride is the same on these, but we've got lithium plus and potassium plus. Those are the 2 differences. Remember, here's the periodic table. So lithium's up here and potassium's down here. Okay, so I'm going to go through and list some of the differences. So between lithium and chloride, right, we talked about atomic distances. There's a distance of 241 picometers. Okay, between potassium and chloride in these big ionic structures, the distance is 314 picometers. Okay, and so in lithium chloride, we have this ionic distance that's smaller. Okay, also between lithium and potassium, lithium is a smaller ion. Which makes sense if it has a smaller distance. And so because it's a smaller ion, it has less energy shells, or it has less energy shells to make it smaller. Okay, and because of that smaller distance, like we have to push these things closer together because they're smaller, it's going to release more energy. Okay, so the bigger the negative number means the more energy is released because they're closer together. Okay, so over here, potassium's bigger. There's a bigger distance between the 2 ions. Potassium has more shells. So remember, as the atoms get bigger, what happens on the outside of the shell don't matter as much. And this has more N shells compared to, or energy shells compared to lithium. And so because of these things, then less energy is released when potassium chloride is formed. Okay, so let's look at another example. So here I have sodium fluoride. So remember, these are the gaseous states. And when I put these two things together, I form this huge network of positive and negatives all lined up together as a solid. The delta H lattice energy equals negative 910 kilojoules per mole. Then I have the calcium +2, oxygen +2 that come together and form calcium oxide, okay? And the delta H lattice energy of that equals negative 300 or 3,414 kilojoules. Notice this number is huge. Okay, why is this such a huge release of energy? And so we look, we've got sodium fluoride right here. When that comes together, it's negative 910 kilojoules per mole. We have +1 and a -1 charge. And then when we have the calcium and oxygen, we're going down the periodic table. So calcium and oxygen's right next to fluoride, right? So why is calcium oxide huge? Okay. And so Coulomb's law states that the lower the charges, the less energy that gets released. Okay, and the reason why is because when you have lower charges, there's less attraction. Okay, and so the stronger the attraction, right? If we have a +1 going towards a -1, they're attracted to each other, they're going to come together and release energy, right? But here, if I have a +2 going towards a -2, these are bigger charges. There's going to be a much stronger attraction. So when these get close together, they're going to come together. And when they come together, it's going to be quick and they're going to release a lot of energy. So lower charges, less energy released, stronger attraction. Higher charges. And here I mean ionic charges. More energy, and in that energy is heat, is released. Okay, let's like put an A in there. So lower the charges, less energy released. Higher the charges, a lot more energy is released. And so I want to do an example of calculating these lattice energies. Okay, so the example, whoops, I moved my notes over here. Okay, so an example of this and how you think about this is the Born Haber cycle. Okay, this cycle is the hypothetical series of steps that we can calculate energy from ionic compound formation. And so I wanted to go through the example of the lattice energy of sodium chloride. Now, remember with lattice energy, there's a very, very specific definition where we have Na plus gas plus Cl minus gas goes to sodium chloride solid. And so the energy that it takes is this delta H lattice energy. Okay. Now, we have to use hypothetical steps to do this because I can't take sodium and I can't take chloride in the gaseous form, right? These are usually solids or aqueous ions. Like if I take and I dissolve sodium chloride in water, I get, so they're solids or they're aqueous ions. And so this reaction doesn't really happen. Like I can't take sodium plus gas and chloride minus gas and put them together. So I have to use knowledge from what I know, okay? And so here I'm going to start with what's the lattice energy of sodium chloride. So I'm going to start graphing this, okay? And the first thing that I want to start with lattice, so lattice energy, again, is sodium plus gas plus chloride minus gas goes to sodium chloride solid, and that lattice energy is delta H lat, right? So I want to find the energy of this reaction. So the first thing I'm going to do is start with something that we talked about many chapters ago, but delta H of formation. Okay, and so I'm going to start with a delta H of formation of sodium chloride. Okay, and you have a table in your book with delta H of formations. Okay, and so the delta H of formation for this is I take sodium metal, right? And I can actually grab this stuff, right? And I take half of chlorine gas, and you guys know chlorine gas is yellow. That's something else I can get. I can take these two things physically and put them together to form sodium chloride salt, okay? And the delta H of formation of this process is negative 411 kilojoules, okay? Or kilojoules per mole. I'm just going to write kilojoules just because it's smaller, okay? And so when I start writing this, I'm going to start here. I'm going to draw a diagram where I have sodium solid plus my 1/2 chlorine gas. And it's going to go through some process. And we're going to end with our products here, which is sodium chloride solid. Okay. And I know from the delta H of formation that the distance between this and this is negative 411 kilojoules. Okay. And we've seen these diagrams before, right? Where energy in kilojoules are on this side. So wherever this starts on the energy diagram, it doesn't matter where you draw it, we're going to end negative 411 kilojoules lower in energy at sodium chloride. Okay. The other information that I have is this lattice energy. Okay, maybe I'll put this in green. And so I want to find the lattice energy, right? That's the whole goal. Now, in order to do that, I have to find sodium plus gas and chloride gas to form sodium chloride. And so that's usually higher in energy. So I'm going to draw this as sodium plus gas plus Cl minus gas. So there's my reactants. And that's going to take some energy. And that energy right there is going to be delta H, lattice energy. Okay. And so I can hypothetically come up with steps to kind of complete this cycle. So I want to know what happens here. Okay. So I know that I have, with lattice energy, I have sodium plus gas and chloride minus gas, right? And I know that whatever energy that releases, right, it's going to release, so we have a negative number, is going to form sodium chloride, right? So I want to find that value. And what I know with delta H of formation is that if I start with physical objects, sodium solid and chlorine gas, then I can form sodium chloride, but it's going to be lower in energy. So what I need to do is find this information right here. Okay, and so I have this next slide where I have my whole diagram laid out, right? So here's my reactants. And they're physical reactants that I can actually hold. And I have products over here. Let's spell products right. Okay, and I know my delta H value is negative 411 kilojoules. Delta H of formation. And I know my delta H lat right here is what I'm looking for. Okay, and so in order to find this delta H lattice energy, I have to go through sodium plus gas and chloride minus gas. Okay, so what that means is I need to find the process to get up there. Okay, So the first thing I'm going to do is look at sodium. And I have sodium solid, and I need to figure out the steps that it takes to get to sodium plus gas. And then the second thing I'm going to do is I start with 1/2 chlorine gas, and I want to figure out how to get that to chloride. Okay, so I'm going to go into my book and look at delta H values in different tables in order to find these processes. Okay, so first step, I want to look for, how do I get sodium solid into sodium gas? Okay, so first step, sodium solid to sodium gas. Well, I know that I can get sodium solid into a sodium gas. Right? I take sodium solid, and this would take a ton of energy. And I would take that sodium solid and heat it as hot as I could and sublime it. Right? So I'm going from solid to gas. So this is delta H of sublimation. And this is a measurement that you can either do in the lab or you can find in a table. Okay, so delta H of sublimation, the first one. Next, I know that if I have sodium gas, I can take and remove an electron to form sodium plus. So sodium gas, I'm removing an electron to form the sodium plus. When I do that, I have a different delta H value, and this is the delta H ionization energy. And I'm removing one electron, or the first electron, that's a positive one charge. So I put a little 1 right there. Okay, if you have to remove more than one electron, you have to do it stepwise. So you go to +1, remove another electron, you'd have an ionization energy of 2. So right here is ionization energy. Okay, so in order for me to go from solid sodium to sodium plus gas, I have to do it in 2 steps. Step 1, I go from sodium solid to sodium gas through sublimation. And when I measure that heat or that energy exchange, it's a delta H sublimation. The next step is where I take that gas and I remove an electron from it. Okay, so sodium gas goes to sodium plus an electron. I've removed the electron, and that I can find on an ionization energy table, the energy it takes to remove an electron. So I look for delta H ionization energy 1. Okay, so I'm going to go back to my graph. So here I have my sodium solid, and my first step is to go from that sodium solid to that sodium gas. And this is going to be delta H of sublimation, right? So that was my very, very first step. And remember, the chlorine gas carries on, so it's going to still be in this process. The next step is my second step, and that's where I convert the sodium gas to the sodium ion gas. And when I do that, I get a delta H of, or for the ionization energy. So I can look up that number. Okay, so now I've gone through and converted all of the solids, or all of the sodium, right? I've gone from sodium solid to sodium gas to sodium ion. I still have this chlorine around. Okay, so next what I need to do is go from this chlorine gas to chloride. Okay, so notice my sodium's okay. I've already converted that, we're good with that. But now I need to figure out the chlorine step. I'm going to go to the next slide. Okay, and so here, when I type, the handwriting's much neater. So here I start with my products, physical products, sodium solid and half chlorine gas. I take and I sublime the sodium. It's going to take a certain amount of energy. When I sublime it, it's sodium gas. Next, I'm going to remove an electron. So I have my ionization energy. And I've just removed one, so ionization energy 1. And I'm left with sodium plus gas plus chlorine Cl2. So my next step, right? So the sodium gas matches that. So I'm good. I've already converted that. So my next step is to take this 1/2 chlorine gas and convert it to chloride. Okay, I'm trying to fill in all of the areas of this cycle, right? The Born Haber cycle. And so I need to do this next process. So when I do this, okay, I have 1/2 Cl2 gas. Okay, the first thing I need to do is take this chlorine, right? Chlorine is Cl bonded to Cl. I'm going to take that and break this bond right here. Okay, so first step is I take my chlorine gas and I'm going to break that bond. When I do that, I just get Cl gas by itself. Okay, when I do this, it's going to take some energy, and that energy is a delta H, and it's called a bond dissociation energy. Okay, basically what it is I'm breaking that bond. So, I looked up the bond dissociation energy, and this is a positive 122 kilojoules. So I got this from a table. And I found that 1/2 chlorine gas, I take that chlorine gas, I break it in half, and I have 1 chlorine gas atom, right? And the energy that it took is positive 122 kilojoules. Okay, my next step is I'm going to start with my chlorine gas. And I need to form chloride. Actually, let me erase this quick. I'm just going to write it lower so I don't run into the other thing. So next step, I have this chlorine gas. And I need to form this chloride minus. Okay, so the difference between these two is an add an electron, right? So I have to add an electron, just one, in order to form this. So this reaction is delta H of Ea. Or electron affinity, okay? So I'm adding an electron, and the heat or energy that's associated with that is the energy for the electron affinity. Okay, so now I've gone from my chlorine gas to my chloride, and I can add that into my cycle. Okay, so I start with my chlorine gas. The first thing I'm going to do is break that chlorine bond. Okay, so I guess I called it step number 1 again, which is the delta H of the bond dissociation energy, right? I'm breaking the bond. And when I do that, I have chlorine gas, or that chloride atom by itself in a gas form. The next step with my chlorine is I need to add an electron to go from chlorine gas to chloride minus. So when I add that electron, it's the delta H of the electron affinity. Okay. So now I've gone through and I've actually completed my whole entire cycle, right? So I started with, I want to know the lattice energy. I started with physical objects I could take, right, with that delta H of formation. And I built a path for me to hypothetically think through all the different arrangements to get up to the definition of lattice energy. So on my next slide, I have every single thing filled in, okay? And so now what I do is take my delta H F, right? So this little dot means standard conditions. I was too lazy and didn't write standard conditions on all of these steps. We're just looking at things under standard conditions. And my delta H of formation is going to equal the sum of all of the steps. So I'm going to look at every single step in my whole entire cycle, and the delta H of formation has to equal all those steps. So delta H of formation equals delta H of sublimation, delta H of ionization energy 1, delta H of bond dissociation energy, delta H of the ionization energy, and then delta H of the lattice energy. Okay, and I put this in bold because this is the variable that I want to find. So the second step to this, okay, so what I've done is I've taken this right here, delta H formation, so this equation where the delta formation equals all of the steps that I came up with, right? And now I'm going to go to the tables and actually look up the values for each one of these numbers. Okay, so the next step is to look up the reactions in all these different tables. So I have delta H of formation, and I know that the delta H of formation is this first reaction right here. Okay, so delta H of formation, I look at my table and it gives me negative 411 kilojoules or kilojoules per mole. Okay, so these units are interchangeable when we're talking about this stuff. The next is delta H of sublimation for the sodium step, right? And so I look this up on a table and I get a positive 108. I look up the ionization energy table and find a value of 496 for sodium. I look up the bond dissociation energy. And when I looked up this value, it was chlorine gas goes to 2 chlorides, but I need just 1. So I need to divide this by 2. I divide by 2. So my chlorine gas so remember in my reaction pathway, I had 1/2 chlorine gas goes to chlorine gas itself, right? So when I looked up the table, this was the equation it gave me, but I know that mine's half that, so I had to take and divide by 2. So my reaction gives me a positive 122 kilojoules. The next step of the chloride was to add that electron. So I added the electron and I got a delta H electron affinity of negative 349 kilojoules. And then my last step was the lattice energy, right? And this one I couldn't look up. And so this is a big question mark. This is what I'm trying to find. Okay, so I have this delta H of formation. I'm trying to find this. Okay, so what I need to do is take and get this lattice energy by itself. So to do that, I'm going to take and subtract every single one of these to move them to the other side. So if I subtract the delta H not sublimation, I subtract the delta H not ionization energy 1, I subtract the delta H bond dissociation energy, I subtract the delta H electron affinity. That's going to make the delta H lattice energy all by itself. Okay, so I've taken all of these values and I subtract from both sides. So I'm moving it over to the side with the delta H of formation. Okay, so I've looked up all the reactions, I've rearranged my equations. The next thing I do is I take my numbers and I put them into the equation. Okay, so here I have this all written out. Okay, so I've rearranged the equation. I have delta H lattice energy all by itself. And now I'm going to take and put these numbers in. So first number is delta H of formation, and that's negative 411 kilojoules. I'm going to subtract the next value, which is delta H sublimation. I'm going to subtract the next value, which is ionization energy. I'm going to subtract the next value, which is this delta H bond dissociation energy. And remember, I had to divide it by 2 because of the way my reaction worked out. The next, I'm going to subtract my activation energy or electron affinity. And that's a negative number. So I'm going to subtract a negative 349 kilojoules. And all of that is going to equal my delta H lattice energy. Okay. So again, I took each of these variables and substitute the numbers into the equation. Okay. I'm going to go to the next slide, and I've taken and I've kind of lined them up a little bit so you guys can see. Oh, so this one is negative times a negative, so this should be positive. I have a typo on my slide. Okay, so I subtract all these numbers, I add this number, and I get a delta H value of negative 788 kilojoules. Okay, so what that tells me is if I were able to collect sodium plus gas and sodium minus gas, and I was able to collect these two gases, and I stuck them together in a container, that I would release, or the reaction would release, negative 788 kilojoules, or 788 kilojoules per mole, in order to form the sodium chloride. Okay, so this is the Born Haber cycle. And basically, we're taking physical reactants that we can put together here, the delta H of formation variables, and hypothetically coming up with a pathway to get to these ions that are gas that we can't really make in order to figure out the energy that's created. Okay, and so this whole process gives us an equation where our delta H of formation equals all of the steps that we need in this process. Okay, so hopefully this helps you guys do an example of the Born Haber cycle. Let me know if you have any questions.